We are going to cover everything that you need to be successful in the propositional logic unit in discrete mathematics. We're going to start with propositions, talk about truth tables, talk about logic laws, talk about logical inferences, and how to translate some sentences into logic. So first, propositions are anything that can be declared as true or false, but not both at the same time. It does not mean that you have to know whether it is true or false, just that it can be one of those two. So, for example, the result of adding two rational numbers is rational. This can be true or false. It is a proposition, and this would be a true proposition. Binary number 0 is used to represent false in logic. This is a fact that can either be true or false. It is a proposition, and in this case, it would be considered true. Is this a proposition? Well, this is not a proposition because this is not a declarative sentence. It's not a statement. It is a question. Is this a proposition? True. Is this a proposition? False. Doesn't really make much sense here. So no, that is not a proposition. What about this? Take this from me and run. True. Take this from me and run. False. That doesn't sound right. This is a command, also known as an imperative. So commands or imperatives are not considered to be propositions, and same with questions, and these are also called interrogatives, coming from the word interrogate. So if you have an interrogative or an imperative, which is a question or command, you are not looking at a proposition, but any sort of simple statement is. Okay, so propositions are either going to be true or false. So typically in, say, a logic book in philosophy, you might see something that looks like this. Where is my green? So I'd have true, and they would have false. But in discrete mathematics, we typically step away from T's and F's, and we use ones and zeros. And that is because there's also a mathematical way to define propositions that we just can't do with T's and F's. So we'll be using this system in this video, ones and zeros, rather than true and false. In digital logic, the same idea is used, but 1 is like an on state and 0 is like an off state. So no matter which type of logic you're working with, there's some correspondence to 1 and 0 we can use. Now, if we have any simple proposition, we can combine them with different operators. So let's say we just have the proposition P, and this can stand for any sentence that we want it to. We can take P and we can negate it. We can make not P. So you'll see it like that, or you'll see it with the little squiggle in front of it to be not P. We have a symbol for and. So let's say we have P and Q. And there's 3 different ways we can see this. We could take P caret Q, so that's the and sign. We could use an ampersand, or we might even use a dot. Typically, though, we would see this form up top. I'll sort of put in boxes the most regular forms that we see. For or, there are 2 different ways you'll see this. Usually in any sort of philosophical or computational logic, we would see the V for P or Q. But in digital logic, you may see a plus sign instead. Or is also called addition in some systems. If we have a conditional, like if then, let's say if it rains, then I will go outside, a classic example, a little twist. Usually we see the arrow here, so saying if P, then Q. And you might see an open horseshoe for this as well, so P, then Q, but again, typically we would see the arrow rather than that horseshoe. Especially in discrete mathematics. The bottom one is really more for philosophical logic and intro philosophical logic at that. The last one, if and only if, 2 ways to show this. P, if and only if Q. This is basically a 2-way conditional. If P then Q, and if Q then P. So we can either use a double arrow, which would be the most common, or we would use the equivalent sign here. And that would be, again, more so in digital logic than in discrete mathematics or in philosophical logic. So these symbols might take a little bit of time to remember, but once you have that pattern down, you'll be fine with recognizing this. So when we create more complex formula, which we call well-formed formulas if they follow the rules, we have to be careful with how we combine things. So for example, any of the things we saw earlier we could do. So if we started with P, we could make not P. Let's say we had a Q here, we could then join them together with the and sign. Let's say we want to put a conditional on top of that, so we could say this is arrow R, for example, and this is also going to be well formed. So this one is good, but there are some examples of bad things. So for example, we cannot just put two propositions side by side without any connective in between them. Another thing we cannot do is we can't just put two connectives back to back like that, or sorry, not back to back, but a connective afterward with nothing to connect it to. That does not work. Similarly, if we do something back to back, like we could not do P and or Q, that would not work either. It has to be proposition with a connective if it's negative, or two propositions and a connective in between if it is one of the binary connectives like and or. Now, we can build these separately. So let's say you had not P and not Q, and then you had not R and not S. We could pretend that both of these are just a Wff, which they are. It's a well-formed formula, and we could put something in between them to connect them. So this is sort of like saying I have something alpha, I have something beta, and I'm joining them together. So that is also valid. Now, the main connective is the one that scopes over the entire formula. So if I just rewrite some of the ones we had earlier, so not P and Q, arrow R, and then we had not P and not Q, and not R and not S. The main connective is the connective that essentially sees everything. So in this first case, and is joining just not P and Q. It's only seeing two things, it's not seeing R. But this connective, the arrow, sees R, and it sees everything inside this complex well-formed formula, so this is the main connective. In other words, this is the final connective you add when you're evaluating your formula. In the example here, not P and not Q, and not R and not S, this and in the middle is the connective that sees everything. So it sees inside both of those complex well-formed formulas, so this would be the main connective. Usually you can tell which one is the main connective just by looking at the brackets. So for example, let's say we had not P, arrow, S, and T. Well, we just take a look at the biggest bracket and we can take a look outside. Oh, look, there's the main connective. It sees everything inside. Okay, so that's how we can find main connectives. Let's take a look at actual syntactic structure. So if we want to really get down and dirty with how we can create these, we can essentially lay them out as a tree structure that shows the process. So I'm doing this one in reverse because usually you'll see a completed formula, not one with a bunch of pieces. So we see what the main connective is. Well, this not is just seeing P and Q. It can't see R, so that's not going to be the main connective. And is in the brackets, it only sees P and Q. This arrow is going to see everything before it and everything after, because if you take two well-formed formulas and put them together with an arrow, that's what it looks like. So the main connective here is going to be the arrow. So what we can do is we can split this up into components. We can take our connective in the middle, and we can break up our well-formed formulas on the left and right. And we can continue this process. So how did we get not P and Q? Well, it's simple. We took not, and then we combined it with P and Q. Now, how do we get P and Q? Well, we took P, we took Q, and we can join them with and. For not R, how did we get not R? Well, we took the proposition R, and we added a negation in front of it. So that is how we could show our well-formed formulas with this sort of syntactic structure. So if you're not quite getting what is a well-formed formula or not, you should be able to break it down, if it is well formed, with a tree like this. So where every branch is either going to be a negation and some proposition, or it's going to be a ternary branch with some sort of proposition on the left and right, and then a connective in the middle. So one of these. Okay, now usually the first main task you have to do is calculate truth using a truth table. And essentially a truth table just lists all possible configurations of truth. So let's say we just had to evaluate P. We know that P can either be true or it can be false. So this would be the beginning of our truth table. But imagine we were actually evaluating two formulas like P and Q. Now we need to create all possible combinations of truth. So there's going to be one case where P is true and Q is true. There's going to be one case where P is true and Q is false. One case where P is false and Q is true. And another case where P is false and Q is false. So you could go through all those in your head, or you could just follow a simple pattern. That is, on the rightmost, alternate 1, 0, 1, 0, go over left one row, double up on them, so 1, 1, 0, 0, and so on and so forth. So if we follow this pattern to see what it looks like with 3 variables, we could, I won't use colors, I'll just alternate because otherwise it will take a while. We could go 1, 0, 1, 0, 1, 0, 1, 0. Why am I doing 8 rows? Well, I'm counting the number of variables and I'm raising 2 to that number. So there's 3 variables, so 2 to the 3 says we have 8 rows. When we had 2 variables, it was 2 to the 2, we got 4 rows. So that's why I'm setting up 8 here. Now with Q, we double up, so we go 1, 1, 0, 0, 1, 1, 0, 0. And then for P, we double up again, 1, 1, 1, 1, 0, 0, 0, 0. And now we should have all possible combinations of truth. So if you don't quite understand why this works, you can watch that part again, or you can wait for a video on counting where we talk about power sets and maybe things will click there. But this just ensures that we have 8 different possible configurations to evaluate. So what do we do with the negation? Well, the negation is like English not. It is not the case that. So if I were to say grass is green, the negation would be, it is not the case that grass is green, or grass is not green. So if we have a truth table, which we set up as just P, so either P is true or P is false, we can then create not P. And what this is going to do is this is going to flip the truth value. So if P is true, then not P is false. If P is false, then not P is true. And there's a nice mathematical way to calculate this. So we can say the value of not P is equal to 1 minus the value of P. So if we put this into the formula, imagine we look at this first row here. We're saying that the value of not P is equal to 1 minus the value of P. Well, P is 1, so we get 0. And that is what we saw there. And in this case, it would be 1 minus 0 since P was 0, leaving us with 1. So this is a mathematical way to figure out what the value of the negation is. Now, the conjunction is like and. So it takes 2 propositions or 2 well-formed formulas and joins them together. In English, we say and, but we can also say but, although, even though, however, in addition to. There are many different conjunctions that work like this in English. So if it's a conjunction in English, typically it means and. So if we set up our truth table with alternating 1s and 0s, so 1, 1, 0, 0, and 1, 0, 1, 0, what we get together is P and Q. And this is true only when both sides are true. So it's true if P is true and Q is true. But if either one of them are false, so in the second row Q is false, in the third row P is false, in the fourth row they're both false, in these 3 cases, it comes out to be 0. It comes out to be false. So P and Q is true only when they're both true. And to figure this out mathematically, what you can do to find the value of P and Q is you just take the minimum of P and Q. So the minimum of value P and the minimum of value Q. So in the first row, for example, we take the minimum of P and Q, which is 1 and 1. The lowest number is 1. Okay, but what about in, let's say, row 3? This would be the minimum value of P and Q. So P is 0, Q is 1, so the minimum value is 0. And that's a nice mathematical way of figuring this out. The disjunction is or unless. So if either one of the disjuncts are true, it could be both, then P or Q will be true. So we can write this as P or Q. So in the first row, for example, P is true, Q is true, at least one of those are true, which means P or Q is going to be true. In the second row, P is true, so at least one of them is true. We get a true output. In the third row, Q is true, so at least one of them are true. We get a true output. But in the fourth case, P is false, Q is false. Neither of those are true, therefore P or Q is false. And the way we can figure out the value of this is instead to take the maximum value of P and Q. So in the case of row 3, for example, we would take the maximum value of 0 and 1, which gives us 1. In the fourth row, we take the max value of 0 and 0. The highest number there is 0, so we output a 0. That's the mathematical way of figuring that one out. Now, the next one is the conditional. So this is an if-then. This is as if you pose what is called a premise or antecedent. This is your condition. And if that condition is satisfied, you get a consequent. So you get your action. So if antecedent, then consequence. So for example, in English, you might say, if you eat your dinner, then you get dessert. So if you satisfy the condition of eating dinner, then you should get dessert. So this is the only truth table that people really struggle with because of the last two values. So let's talk about the intuitive one first. So if P happens, then Q happens. That makes sense. That's a conditional. If you eat your dinner, then you get dessert. So P arrow Q should be true. Now, what happens if you eat your dinner, but you don't get dessert? So P is true and Q is false. Well, that means that the conditional didn't hold because you were told if you eat your dinner, then you get dessert. You've eaten your dinner and now you're not getting dessert. This is not a true conditional. You've been lied to at some point. Now here's the question. If you eat your dinner, you get dessert. What happens if you don't eat your dinner? Now, your parents might have told you when you were a child that means you don't get dessert, but logically that is not true. So logically, both of these are true because we cannot verify that the condition will break. So if you don't eat your dinner, we have no idea whether you get dessert or not. If you don't get dessert, that's fine. But if you do get dessert, that's fine too. There was no condition that said if you don't eat dinner, then you don't get dessert. So these two last lines are probably some of the most unintuitive ones. If you're not quite getting the intuition, I tend to recommend the mathematical formula, which says that a line is true if and only if the value of the antecedent P is less than or equal to the value of the antecedent Q. Sorry, the value of the consequent Q. So in this case, 1 is less than or equal to 1, therefore we get 1. 1 is not less than or equal to 0, so we get 0. 0 is less than or equal to 1, so we get 1. 0 is less than or equal to 0, so we get 1. So this is a nice little mathematical way of determining that. And we'll talk more about conditionals later in the video. The biconditional is an operator that expresses that both P and Q have the same truth to them. So P and Q are either both true or they're both false. It's basically saying you have P arrow Q and you have Q arrow P. So we write this with the double arrow, which is just a great way to symbolize both directions. And it's true when both the values are the same. So it's true in the first row when they're both true, and it's true in the last row when they're both false. But the rows in the middle where they differ in values, this is where we get our falses, because P is not the same truth as Q in the second row. P is not the same truth as Q in the third row, so these output to be false. And in English, typically you hear if and only if, but it can also refer to just in case that, which I don't have much intuition about personally to make it make sense. That is the language that I'm told how it works, but it's not quite intuitive to me still. I understand it, but I don't really grasp the intuition behind it. So typically I stick with if and only if as the translation for it. So let's put this together. Let's make a larger truth table for this. So how can we figure out the truth of P and Q or not P and not Q? Well, here's what I'll need to do. I will need to create a row for P, a row for Q, column for not P, a column for not Q. I'll have to get P and Q together. I'll have to get not P and not Q together. And then I'll have to put them all together to get P or Q and not P and not Q. Okay, so let's just make all of our columns here. And for the sake of it, just to make it look nice and organized, we'll make the 4 columns. So we'll set this up with P's and Q's being 1, 1, 0, 0, and 1, 0, 1, 0. And now we'll go step by step and watch the truth values change. So here we're doing not P. And remember, not P is the flipped version of P. So if P is true, that means not P is false. Same in the second row. In the third row, P is false, so not P is true. It should be green. And in the fourth row, P is false, so not P is true. So this is the first one done. Now we're going to do not Q. So same thing, we're going to flip the values. So Q is true, so not Q is false. In the second row, Q is false, which means not Q is true. And the third and fourth row show the same pattern. So 1 flipping to 0 and 0 flipping to 1. Okay, so we have all of our bases covered. Now we need to start putting things together. So let's do P and Q. So we're taking a look at these 2 rows, those 2 columns, and looking at P and Q. So it's true when both P is true and Q is true. So this happens in the first row, where P is true and Q is true as well. In the remainder of the rows, so in row 2, Q is false, so P and Q will be false. In the third row, P is false, so P and Q will be false. And then in the fourth row, they're both false. Okay, so that column is now complete. Now we'll do not P and not Q. So this time we're taking a look at these 2 columns and putting them together with the conjunction. So in the first row, not P is false, so the conjunction will be false. In the second row, not P is false, so the conjunction will be false. In the third row, not Q is false, so the conjunction will be false. But in the fourth row, not P is true, not Q is true, therefore the conjunction of those is true as well. Now, the last thing we have to do is combine it all together. So P and Q or not P and not Q. So we're going to take a look at these 2 with or in between. So it's going to be true if either one of those 2 columns is true in a row. So in the first row, yeah, P and Q is true, so at least one of those is true, therefore the row will be true. In the second row, neither of them are true. Same in the third row, so those will be false. And finally, in the fourth row, not P and not Q is true, therefore the disjunction of both of those will come out to true as well. So this is our final result. It is true when P and Q are both true or when P and Q are both false, and it's false in the other circumstances. So if we remember earlier, we saw a truth table for P if and only if Q, and we had a similar pattern. We had a 1, 0, 0, 1 truth table. So what we can say is that these are really just different ways of writing the same thing. They have the same meaning when it comes to truth. So I think that's pretty interesting. We'll talk more about that officially in a bit. For now, let's try one more. So how will we set this up? We're going to need P, we're going to need Q, we'll need not P and not Q again. We'll have to do Q arrow not P. We'll have to do P and not Q. And then we'll have to do Q arrow not P, arrow P and not Q. So once again, we'll just set this up so that way we have a nice clean table. And then I will fill in some of the things that we had already done. So let's just get those dotted lines for our 4 rows. So I'm just going to speed through some of the stuff that we learned from the previous question. So if you do these a lot, you just know these truth tables sort of off the top of your head, or you can calculate them pretty quickly. Now, Q arrow not P is where we're really starting here. So we're taking a look at Q and going to not P. So remember, the conditional is going to be false when we have 1 arrow 0, and everything else will be true. So if we see 1 arrow 0, we write false. Anything else, it is going to be true. So the first row, we have 1 arrow 0, so this will be false. In the second row, we have 0 arrow 0. Okay, that will be true. In the third row, we have 1 arrow 1, which will be true. And in the fourth row, we have 0 arrow 1, which will be true. So there's just one condition here where it is false. Now let's do P and not Q. So which ones are we looking at now? We're taking a look at these 2 columns. So it's true when both of those are true. And if we just scan row 1, we have 1, 0, so false. Row 2, we have 1, 1. There we go, both of those are true. And then in the third and fourth rows, those both come out to be false as well. As you can see we have a 0, 0, and a 0 in these cases. Now the final one is about putting them together. So which 2 columns together? These 2 columns. And we're going from left to right. So again, if we see 1 arrow 0, we know it's false. Anything else could be true. So first row is 0 arrow 0. We just put a little arrow in there. We can see what we're doing here. We have 1 arrow 1, which will be true. And then in the other 2 rows, we have 1 arrow 0, which comes out to be false. So this is the final set of values for that well-formed formula. And if we take a look at another column here, it's really just the same thing as P. So we don't need to write this complex well-formed formula out. We could have just written P instead, and it would have the same truth conditions. So that's how you can do truth tables in propositional logic. Next, we're going to classify our well-formed formulas. So when you finish a truth table and get the values for your complex Wff, what's going to happen is you'll get a series of numbers. If all of the numbers in a column, so let's just create a little example here. Let's say we have a table like this, and we have a formula like T. And let's make a formula with an upside down T, and let's use one like P. So if it is a tautology, this means it's always true. So the whole row would be, so the whole column would be once, so 1 in every row. Some examples of this are like P or not P, or not P and not P, or even just P arrow P. These would all be examples of tautologies. And when you do the truth tables, you'll find out that all of the rows end up being 1. If you have a contradiction, that means it's always false. So we actually use the upside down T, this is called the falsum, to signify this, and it would look like this. Every single row has a 0 in it. So some examples would be P and not P, so something can't be true and false at the same time. You could have not P arrow Q arrow P. This would be another example of a contradiction. You could do not P or not P. Basically, the negation of any tautology will be a contradiction. So that's another way you can look at it. A contingent formula is something in the middle. So that means somewhere there's a true and somewhere there's a false. It's not all ones or not all zeros. So you might have something that looks like this, for example, and that would be an example of contingency. So little arrow there. So a lot of formulas are going to be contingent, like say P and Q, or if P then Q, or R and S and not T. These are all examples of contingent formulas. And if you do the truth tables for these, you will find out that final column has both ones and zeros. Now, if two well-formed formulas are logically equivalent, they will have the same output. So we've seen this before. Let's just fill this in. Let's say we do P arrow P. We're going to do not P. We'll do P or not P. We'll do P and not P. And then we'll do not P and not P. And we're going to see which ones are equivalent to each other. So P arrow P is the first one. So we get one arrow 1 in the first row, which gives us true. One arrow 1 in the second row, which gives us true. We're going to get 0 arrow 0 in the third and fourth rows, and both of these come out to be true. So P arrow P is a tautology. It's all ones. What about the negation of P? Well, we just take the first two, well, we take the value of P and we flip it. So the first two rows P is true, so in the last, so not P will be false. In the last two rows P is false, which means not P will be true. Okay, now we can do P or not P. So just if one of them is true, then P or not P is true. So these two columns we're looking at. So in the first two rows, P is true, and in the last two rows, not P is true. So all of those are true. Okay, now let's do P and not P. So I didn't want to get rid of my things there. Okay, P and not P, which means that both of these have to be true in order for P and not P to be true. But in the first two rows, not P is false, and in the last two rows, P is false. So they're all false. That would be a contradiction. Now finally, we have not P and not P. So what we're doing right now is we're taking a look at the previous row and we're just, previous column, sorry, and we're just going to flip the values. So these are all ones. Now what this means is that some of these are logically equivalent. As I just demonstrated before with tautologies, P arrow P, P or not P, not P and not P, these are all equivalent. They're all tautologies. The outputs in the rows are the exact same. So we could do this with more complex well-formed formulas, which I'm sure you will do at some point. Now, I've said I'd talk a little bit more about conditionals, so here they are. The conditional starts out with P arrow Q, and there are three different variations of it. So, for example, with the inverse, what we do is we negate both values. So if we have P arrow Q, the inverse of it is not P arrow not Q. If we were to do the converse, so inverse is like negate, converse is a flip, which I shouldn't say a flip because I'm using that for truth values. Let's call this a swap. So we get Q arrow P, and then when we say the contrapositive, this is doing both at the same time. This is a negate and swap. So what we end up with when we start with P arrow Q, the contrapositive is not Q arrow not P. I see that I wrote the not again. Now some of these are equivalent to each other. In fact, the inverse is equivalent to the converse, and the conditional is equivalent to the contrapositive. So if I were to show you a truth table of these, so I am going to skip some of the steps here, but let me just get this table set up with the way that I know how to do it. So our final result for both of these truth tables is going to be the same. And you can verify that for yourself if you'd like, but the values are the same, so the conditional and contrapositive are equivalent to each other. And if you take a look carefully at the inverse and the converse, it really follows the same pattern. P has been negated and the position has swapped. Not Q has been negated and the position has swapped. So really the inverse and the converse are just a contrapositive of each other. So we have to be careful that we get our equivalences right. Because if you're saying that P arrow Q is the same thing as Q arrow P, that's not going to be true. If you're going to say P arrow Q is the same as not P arrow not Q, which is how most people's brains work, that is also not true. It's only equivalent when you negate it and flip it. So that's a little bit more information about conditionals. Now, we don't always have time to draw out truth tables. Instead, we might want to take a formula and manipulate it without having to evaluate truth. So if we know that two well-formed formulas are equivalent, we can make substitutions. So the first one is De Morgan's law. And what De Morgan's law says that if you have not both P and Q, it's logically equivalent to not P or not Q. And here's how you can think of this in English. Let's say I am not both happy and excited. So what does that mean if I'm not both happy and excited? It could mean that either I'm not happy, let's make that Y a little bit more Y-like, or I'm not excited, because I'm not both happy and excited. So I must not be one of those two. And if we think about how this looks, so not H and S with the not outside the brackets, or not H or not S. So we can use some English to help us understand this. If we flip the ands and ors into Morgan's law, we get something equivalent. So not P or Q is going to be the same thing as not P and not Q. So this is like saying I'm neither happy nor sad. That means I'm not happy and I'm not sad. Okay. One way I like to think about these when I see De Morgan's laws is I just push the negation through to all of the letters, and then whatever the sign is, I flip it. So P becomes not P, Q becomes not Q, and if there's an or, I change it to and vice versa if I'm looking at that first law. The distributive law is a lot like how it works with multiplication and addition. So if I have P and Q or R, it's a lot like saying 3 times 1 plus 2. This is the same thing as 3 times 1 plus 3 times 2. So P and Q or R is the same thing as P and Q or P and R. So I can even highlight the X's here and correlate them with the ands so we can see how they match up. In fact, I will do it with the ors as well. So the ors here correspond to the plus sign. Now, it doesn't matter whether these are ands or ors, so it can be P or Q and R, and that will just flip these as well. But what matters, though, is that the two, P and Q or P or Q and R, what matters is that they're different. So if they're different, you can use this law for expansion, or you can take something more complex and factor something out and turn it into a simpler form. We have the contrapositive law as well, so we just saw this. If you have P or Q, you can replace this with not Q, arrow not P, and we'll see a use for this later. The conditional law is a nice alternative for the arrow. If we have P arrow Q, we can say this is not P or Q. And the reason this works is because if we think about the truth table for P arrow Q, I won't use the line tool because I'm doing this quickly here. This will be 1, 0, 1, 1, so let's fill in our zeros now. When is P arrow Q true? It is true in the rows where P is false, so this is not P. It's also true in the rows where Q is true, so in this top one, and we're sort of doubling up here, so that's Q. It's true in either of those conditions, which is how we get not P or Q as an equivalent. And you could use a truth table and verify this as well, that they are equivalent. But this is an incredibly useful substitution depending on what you're doing. The last one I really want to talk about here is what's called the associative law. This just says that if you have three well-formed formulas connected with the same and or, then what you can do is you can move the brackets around. So you can choose who the brackets associate with. And this works the same with ors as well. Just ands and ors. Don't do this with the conditional. That totally changes things. Now, what are all these things used for? Well, in the end, especially in philosophy, it's really about arguments. And in mathematics, it's sort of the same way, but you use it in a much more abstract manner than you would, say, in philosophy. So here's the example. Let's say we had a sentence like, all dogs are brown, Fido is a dog, and therefore we want to conclude that Fido is brown. Well, this is an argument. So what it means is that you have premises or assumptions. So let's say we have two premises or assumptions here, and then we have a conclusion. And the idea is that the premises together with inferences will logically allow us to deduce the conclusion. So what we normally do is we translate English into logic. So that way we can use rules and work with them by evaluating truth. So we're taking natural language and we're working with it in the language of truth. So this is more of a argument for quantificational logic than propositional logic, but let's take a look at what that looks like. So the first thing is going to be just practicing translating into logic. If you can't do the translation, you're not going to be able to do any of the actual deductions with it. So if 6 is rational, it is the sum of two rational digits. So we could say 6 is rational is maybe by R. We'll call that proposition R. And it is the sum of two rational digits. That could be, say, S for sum. Now we have a connective here, if. So if 6 is rational, if R, then it is the sum of two rational numbers, then S. So we could translate this as if R, then S. And a little hint here is that the thing that comes after if, unless there's the word only in front of it, this is going to be the antecedent. But you can also look for the hidden then in order to find the consequent. So that might be an easy way to help you identify which side of the arrow your proposition should go. Okay, this next question says 6 is rational or 6 is irrational. So we'll use R again for 6 is rational. Now, how do we translate 6 is irrational? Well, we might think to use a different letter for this, but irrational, the ir is just another meaning of not. So this is really a negation here. So 6 is rational or 6 is not rational. And what's our connective? It's or, so we put an or in between. So if you just write this out, we get R or not R. I'll just box those in when I'm done. Okay, let's just get rid of some of these markings to make the page a little bit less squished up. Okay, move that. Next one, 8 is an even integer, but it is not divisible by 6. Okay, so 8 is an even integer. Let's call this E. It is not divisible by 6. So I'm going to say it is divisible by 6 is D for divisible, and this not is going to negate it. Now we have one word to take care of, which is but, and but is similar to and, so 8 is an even digit. 8 is an even integer, and it is not divisible by 6. So we can put an and there. So our final result will be E and not D. Okay, what about this last one here? Although 7 is rational, the square root of 7 is not rational. Okay, so 7 is rational, let's call it R. The square root of 7 is not rational. So the square root of 7, we're now talking about a different number. So we can't use r for 7 is rational because we're talking about the square root. So let's just pick a letter like s for square root. And we still have a not in here, so I want to take that not to negate s. Now here's the question. What's our connective? We have r, we have not s. The only word we have left to deal with is although. But it's not in between r and not s, it's just out front. So what does this mean? Well, although is still and. 7 is rational and the square root of 7 is not rational. And if we want, we could even move it in our minds to make the sentence sound more like the logic. 7 is rational, although the square root of 7 is not rational. Okay, so we could do that. And that would give us our paraphrase to get R and not S. So that's just some basic translation practice. And normally in a propositional logic course, you really don't get that much more challenging. Maybe the statements look like mathematics with a lot of symbols in them, but the core idea is still the same. If you're taking a course in philosophical logic, they're going to be much more challenging, and I have an entire series dedicated to that, so please check that out on this channel. Now, all of this builds up to logical inference, which is really the ultimate goal here. So we get premises, we make inferences, and we get to our conclusion through deduction. So what are the rules we have at our disposal? The first rule we have is modus ponens, and this says if we have P and if we have P arrow Q, that means we can deduce Q from it. If you eat your dinner, then you get dessert. I ate dinner, therefore I get dessert. Okay, modus tollens is very similar, but it works in reverse. So let's say we have not Q and we get P arrow Q. Well, remember, we can never have 1 arrow 0 because that gives us a false output. So if we know that Q is false, what does that mean that P has to be? P has to be false too. So that way it can still be true in the end. So if we have not Q and P arrow Q, we can there conclude that not P will be true as well. Okay, disjunctive syllogism. This is an interesting one. It's one of the more intuitive ones in my opinion. Imagine we say P or R. So one of those has to be true. It turns out that R is not true. What can we conclude? Well, that means that P has to be true. Basically, one of these symbols is canceling one of our disjuncts out, which forces the other one to be the true disjunct. So that's called disjunctive syllogism. Sometimes in textbooks it's referred to as just elimination, but that's not really a good name for it, and I'll show you why now. Because we typically use words like introduction and elimination for other rules, and these might have other names in your textbook, but it's still the same. So conjunction introduction says, imagine we have P, imagine we have Q, they're both true, therefore we can join them together and get P and Q. I think that one's a little bit more intuitive. For conjunction elimination, let's say that both of these are true. So P is true and Q is true. What can we conclude? Well, we can conclude that P is true. If they're both true, then clearly just one of them on their own is true. We could also conclude that Q is true as well. So we have two options for how we want to use this rule. The last one on this page is disjunction introduction. So let's say we have P. What can we conclude from this? Well, if P is true, this means that P or anything else will be true as well. So if we have P, we can introduce P or Q. Now, why would you ever want to do this? Well, imagine I told you that if you have P or Q, you get S, and you have P. Well, you need to somehow get this in order to use modus ponens to figure out what S is. So you would use disjunction introduction in order to get S out of it. Now, two more rules. Again, we've seen one of these before. Double negation is pretty straightforward. If you have two negatives, it makes a positive. So we're just getting rid of not. I'm not happy. It means I'm happy. Contraposition, same thing we've seen before. We have P arrow Q. We can therefore conclude that not Q, arrow not P. So it's equivalent to its contrapositive. And really for this top one, I should write it more like that. Okay, so to wrap this video up, let's take a look at 2 examples. They're not too difficult. Again, I have more specific videos on my channel for every single one of these topics. It's just the ultimate guide. So you can check that out if you want harder questions, but here we go. Let's prove that this argument is valid. Let's take our assumptions, use deductions, and get not R. Okay, so I have P and Q, Q arrow S, not R or not S. I see an arrow here. So I want to do my best to get Q. So how can I get Q? Well, let's number these. So 1, 2, 3. So in line 4, I'm looking at line 1. I'm saying P and Q. Well, I know that both P and Q are true, so I can get P from it. So I call this conjunction elimination. Now, well, I didn't really need P now, did I? So why would I grab P? Let's forget about P. I want a Q. Let's get Q. Sometimes you notice you grab something you don't need. So why write it down if you don't need it? Let's just get Q. Now in line 5, we can finally do modus ponens. So we have Q arrow S and we have Q. Therefore, we can get S. So this is modus ponens. And now we have S. Well, let's take a look at this. We have not R or not S, and we have S. So we know that this disjunct can't be true. What must be true? It must be not R. And this is from our disjunctive syllogism. So that wasn't too many more steps. We just need to make 3 inferences and we could get to our conclusion. Now, one more. Not P and Q arrow S, not S or R, and not R. Okay, I see the same thing we had before. I love seeing a good old disjunctive syllogism. Not S or R, we have not R. So what does that do? That forces not S to be true. So not S, and that was a disjunctive syllogism. Now what do we have? Well, we have not S and not P and Q arrow S. So we could use the contrapositive law to rewrite this first, or we could use modus tollens. So the consequent is false, therefore the antecedent must be false. So we can write, therefore not P and Q, and we can just write modus tollens here. Modus tollens is really just an application of the contrapositive law and modus ponens together. Okay, I have not P and Q. I got this not out front, so let's use double negation to get rid of it. And oh look, from that we have proven our conclusion. If we have not P and Q arrow S, not S or R, and not R, we can then prove P and Q. So that is it for the ultimate guide on propositional logic. If there's anything I didn't cover, you can leave it in the comments below, or search through the other playlists on discrete mathematics, or on logic in philosophy and computing science. So that is it for this video. Come back for the next one. If you enjoyed, do all the normal stuff, and I'll see you later.